Yeah, so I'm talking about some joint work with Jaime Even-Zohar, Lakrec, Matteo, Parisi, Ron Tessler, and Lauren Williams. So Ron was the previous speaker, and then Matteo and Lauren are in the room. Right, and so I'll just jump right into it. So I am going to be repeating a little bit of background material that's sort of been covered by various speakers over the past 2 days. I'll go a little bit quickly. If you would like me to slow down for any of it, please ask. Otherwise, I'll just go at the speed I'm going. Right, so the first thing, start out with, so I'm talking about the amplituhedron. So first I have to talk about the Grassmannian of K-planes and n space, and an n-dimensional space. Just like Yelena, I always think about points in the Grassmannian as being represented by a full rank K by n matrix. I also think about the Grassmannian as being endowed with Pluker coordinates. So these are just the maximal minors of my representative matrices, right? And this embeds the Grassmannian into a high dimensional projective space. Okay, and I'm going to care particularly about this very exceptionally nice subset of the Grassmannian called the TNN Grassmannian, introduced independently and in very different language by Lustig and Postnikov. Postnikov's definition is the one we've been talking about this whole time, so I'll give it again. So the TNN Grassmannian is all of those points in GRKN whose Pluker coordinates are non-negative. And I don't know if we've seen a picture of it yet, but this is basically the only TNN Grassmannian that I can draw. It's TNN GR13. So sitting inside of GR13, so this is lines in C3 or R3, so it's the same thing as the projective plane. And this totally non-negative Grassmannian, as you can see, is just a triangle, a simplex. And looking at this, you can kind of see there's a very natural stratification of this TNN Grassmannian into pieces according to which Pluker coordinates are positive and which ones are 0. Right, so the interior of this simplex is where all of my Pluker coordinates are positive. And I also have other strata for different 0, non-zero patterns of Pluker coordinates. Okay, so this stratification is very natural. It also has some more notation that goes with it. We're going to care a lot about this stratification in this talk. So each one of these strata is called a positroid cell. Right, so again, each one of these, I'm just collecting all those points in the TNN Grassmannian with a prescribed 0, non-zero pattern of Pluker coordinates. The word positroid was coined by Alex Postnikov. It's a portmanteau of positively realizable and matroid. And each one of these strata is actually a cell. So it's homeomorphic to an open ball, just like we saw in the simplex case. Right, and so, yeah, so this was proved by Postnikov using his definition that these were positroid cells, and Connie Reach using Lustig's definition. Okay, so, right. I think Yara, yeah, so Yara sort of alluded to these things, but maybe didn't go too much into detail. Okay, and positroid cells, these pieces of the TNN Grassmannian, have a number of different indexing sets. So one thing you can do is you can just index a positroid cell with which Pluker coordinates are positive there. Okay, so that's one indexing piece of information. I'm going to use instead Plabic graphs, like Christina talked about in her lectures. So right, I should also say many of these indexing sets, including positroids and Plabic graphs, were also due to Postnikov. Okay, so what is a Plabic graph? Just as a reminder, it is a planar bicolored graph embedded in a disk with n boundary vertices 1 through n, labeled clockwise. Okay, so I'm not going to tell you how this works, but if someone hands you a picture like this, one of these Plabic graphs, there is an explicit combinatorial recipe to output a cell in the totally non-negative Grassmannian. So if someone handed me this graph, the cell I would give them is this. So points in the Grassmannian represented by matrices of this form, where these Greek letters, alpha through epsilon, are just ranging over positive real numbers. Okay, so throughout this talk, if you ever see a graph, you should be thinking, that gives me a positroid cell. And actually, something even more is true. This graph gives me a specific parametrization of the points in this cell. And that will also kind of be important, but in the background. Okay, so we've got these positroid cells. I'll be indexing them using Plabic graphs. The other thing that's very good to know is not only does the TNN Grassmannian consist of these very nice pieces, but the pieces also glue together extremely nicely. So this was a conjecture of Williams. She proved a combinatorial version, and then Galatian Karp and Lamb used her results and more to prove the geometric statement. So the statement is that TNN Grassmannian is homeomorphic to a closed ball, so kind of like the simplest kind of topology you can imagine, and it's a regular CW complex. So this is a statement about how the cells fit together. I'm not going to go into what it means, but basically it means that when you're gluing these cells together to get the whole TNN Grassmannian, you're doing kind of the absolute most naive thing possible, where you're really just like sticking balls together. You're not doing any funny twisting on the boundary. Sometimes people say this is like the next best thing to a polytope. So it's not linear, but it's sort of, yeah, still just like sticking balls together. Okay, so that's a TNN Grassmannian. Hopefully relatively comfortable with that after many talks defining it again and again. That's the object in the background. And of course, now I move to the amplituhedron, the object in the foreground. So this is the image of a TNN Grassmannian under some linear map. Specifically, the linear map induced by matrix multiplication by a fixed positive n by k plus m matrix. Okay, and the way that I choose these parameters is to make my fixed helper matrix Z, it's tall and skinny. Yeah, so this is n and this is k plus m. Not super legible. Okay.
Actually, like in this, do you assume that Z is only maximal minors are positive or only?
Yes, I'm sorry. Only maximal minors are positive. Yeah, I think you can do some tricks to reduce to the case where everything is positive, but you don't, that is not an assumption you need to define the amplitude. Okay, so, right. So this helper matrix Z induces a map on the TNN Grassmannian by matrix multiplication, and the amplituhedron is the image of the TNN Grassmannian under this map. Okay, so one thing I want to emphasize, which maybe has not been emphasized a lot yet, is that though this map Z tilde is linear, so it's like induced by a linear map, but also if I express it in terms of Plücker coordinates, it's a linear map. So though that's true, the domain is not linear, right? So I showed you a picture of a TNN Grassmannian, which was a simplex, but this is very unusual. Usually, I mean, right, so usually the Grassmannian is cut out by these quadratic Plücker relations. So it's some sort of like surface, right, some curvy thing. And then I'm just asking that all those Plücker coordinates are positive. So I've sort of got this like curvy Grassmannian, then I'm intersecting it with like a positive orbit. So in the end, I get something curvy. So what I'm doing here, yeah, I'm taking like some curvy thing, I'm hitting it with a linear map, and the image is going to sit in another curvy space. Okay, yeah, so it's not usually linear at all. It's not a polyhedron. The amplituhedron is full dimensional in its ambient Grassmannian. So it's k times m dimensional. Okay, and we saw this picture in Yelena's talk, but just to give the easiest example, right, so I just said, usually the amplituhedron is not linear, but in this case that I'm showing you, it is linear. It's all right. Yeah, so k equals 1, m equals 2. The amplituhedron is just a polygon sitting in the projective plane. And then maybe most other circumstances, it's not something you can draw and not maybe something you can think about that. Okay, so I hope all of that was pretty familiar. Pause a second for questions. All right, I'll keep going. Okay, so as Yara said, kind of much more eloquently than I could in his initial talk, the motivation behind the amplituhedron. Okay, so first of all, we're in the physically relevant case, the kind of place where there's physics motivation, we always ask for m to be 4. And in that situation, like the reason behind the definition of the amplituhedron was to give a geometric interpretation of scattering amplitudes in planar n equals 4 super Yang-Mills. And in particular, to give a geometric interpretation for a particular way of computing scattering amplitudes, this BCFW recursion. Right, so inspired by ideas of Hodge's, what they were looking for was an object whose volume should be the scattering amplitude, and you should be able to decompose the object in a way that sort of corresponds to the BCFW recursion for computing the scattering amplitude. Okay, right, and so of course, the object that they came up with was the amplituhedron. And this talk is really about kind of how well does the m=4 amplituhedron kind of fulfill this motivation? And the answer is like, it fulfills it really well. Yeah, so spoiler. Okay, right, so yeah, so this is really like the focus of the talk, is sort of this idea. Okay, so, and I'm going to redefine something that Rand talked about kind of in this context. So I said kind of the goal was for certain decompositions of the amplituhedron to correspond somehow to the BCFW recursion. And so what kinds of decompositions do I want? Well, just from a mathematical perspective, so the amplituhedron is the image of this TNN Grassmannian under some map. The TNN Grassmannian has this very well-behaved decomposition into positroid cells. And so kind of a natural sort of decomposition to look for is one that the amplituhedron inherits from the decomposition of the TNN Grassmannian. Meaning, maybe it's natural to think about decompositions of the amplituhedron into images of polytroid cells. And that's what we're going to do. Right, so the other constraints that you might want to put on your decomposition is they're supposed to help you compute this volume. Okay, and so if you're trying to find the volume of something big, how can you do this? Well, one way is you should break this big object up into smaller, simpler, full-dimensional pieces whose volumes you understand, right? And then to find the volume of the big thing, you just add up the volumes of all the little things. Okay, so yeah, so that's exactly kind of where we're going. Our decompositions are going to be into full-dimensional pieces, and there'll be pieces whose volumes we should understand already. Okay, so to start saying this more precisely, right, so I'm only going to be interested in images of positroid cells. So my notation for that is this. Sometimes I'll take their closure, in which case I'll use this notation instead. Okay, and the pieces that I'm going to use in my decomposition are the tiles, what I call tiles. So a positroid cell image is a tile if it's full dimensional in the amplituhedron, so k times m dimensional, and the z tilde map is injective on the positroid cell that I'm looking at the image of. Okay, so the full dimensional thing is what I said earlier, like we're always interested in computing volumes, so we want to decompose into full dimensional pieces. And then this injectivity assumption has to do with getting pieces whose volumes we understand. I'm not going to go into detail, but that's where the injectivity assumption is coming from. Okay, so those are our pieces, these tiles. And tilings are the kind of decomposition we'll be interested in. So a tiling of the amplituhedron is just any way of breaking the amplituhedron up into tiles with disjoint interiors, right? So non-overlapping tiles. Any questions? All right. So let's think about this easy case, k = 1, m = 2. This is like the toy case. So I said the amplituhedron is just a polygon. So it's two-dimensional. So for tiles, I'm looking at positroid cell images, which are two-dimensional, and the z tilde map was injective on the cell. Okay, and let's think about this a little. So, okay, so if I'm looking for a two-dimensional image where the z tilde map was injective, that means I should also be thinking about like two-dimensional cells in the domain. So two-dimensional cells in the domain, I get those by picking exactly 3 coordinates, say x1, x2, x3, of my of this vector to be non-zero. So if I have such a, I'm looking at subspaces spanned by vectors like this, where all the other coordinates are 0. So if I take the z tilde image of this point in GR1n, what I get is x1 z1 plus x2 z2 plus x3 z3. So in this polygon, where this point lands is somewhere in the triangle, whose vertices are Z1, Z2, and Z3. Okay, so that's what the image, okay, right. And so if I'm sweeping out the whole cell, I'm letting x1, x2, and x3 vary over all positive real numbers. And so my point that I'm getting in the triangle is actually sweeping out this whole triangle. So the images of two-dimensional positroid cells in this amplituhedron are exactly just triangles sitting in the polygon. Okay, and I actually claim that the Z tilde map is injective on each one of these two-dimensional positroid cells, because if I pick a point in a triangle, I can recover, right? So I can write it as a linear combination of Z1, Z2, and Z3, and the coefficients of that linear combination let me invert the Z tilde map. They let me go backwards to a point in the domain. Okay, so great. That means that for this particular example, the tiles are actually just the images of any two-dimensional positroid cell, and they're also exactly triangles inside of this polygon. So tilings are exactly the same thing as triangulations. Okay. Okay, so this is m equals 2, and we're only going to be thinking about m equals 4, so I'll basically stop drawing pictures.
Actually, can I ask you about the previous slide again? So for example, we find down just require that it's so theoretically they cover.
That's right. I don't care about boundary interaction at all. I just care that the interiors are disjoint. Yeah.
But you assume that for tiles, each tile it has a degree 1.
Yes, that's right. Yeah.
This notion depends on Z.
So
Tile depends on Z.
yes, but
Like not as an example I showed it's independent, but in general it depends on.
yeah, so a priori it depends on Z. We do not yet have any examples of a tile which is like a tile for one Z, but not all of them. So all of the tiles we know about are tiles for all Z. For m equals 2, that's just true. Like we've characterized the tiles and it doesn't depend on Z. And for m equals 4, we know some tiles and they all work for all Z. Yeah, good questions. Okay. So I'm interested in these tilings, and because I'm thinking about m equals 4, and kind of going back to this original motivation, I'm going to care, well, the punchline of the talk is that we have tilings that come from this BCFW recursion. So yeah, the punchline of the talk is the BCFW recursion does produce tilings. So let me now tell you how you should interpret that statement. So first, what is the BCFW recursion? I'm not a physicist, so I'm going to give you my mathematical version, which is primarily combinatorial. Okay, so what can I say about the BCFW recursion? Well, if you run it all the way down, it will give you a sum of rational functions, which is equal to the scattering amplitude. Okay, and I'll call such an expression, such a sum of rational functions, a BCFW expression. So just an expression for the scattering amplitude coming from this recursion. Okay, so each term in the BCFW expression, in any BCFW expression, is labeled by a playback graph. Yeah, maybe I'll kind of skip ahead. So yeah, I'll go more into this later, but each term in this recursion is labeled by a playback graph. And I told you before, if you hand me a playback graph, you should think, positroid cell. So each BCFW expression gives you a bunch of positroid cells, and you want the images of those cells to give you a tiling. Okay, so yeah, so I jumped ahead maybe. First, just what does the recursion look like? So pictorially, it looks like this. This is one step in the recursion. So I'm going to pick some index, special index I, and then the BCFW recursion says my amplitude can be expressed in this manner, where over here, I'm summing over kind of all the terms or all of the graphs that appear in a smaller BCFW expression, right? So my G prime is running over some smaller BCFW expression. And then over here in this sum, I'm summing over like this second choice of index J, and then again, these smaller graphs, GL and GR, are running over terms in a smaller BCFW expression. So in order to actually get the BCFW expression out of this recursion, like I have to perform the recursion many more times to determine what G prime, GL, and GR. Okay, and one thing that I'll mention is that at each step of the recursion, you get to choose an I, and the choice of I at each stage will impact the final expression that you get. So this process produces many, many, many expressions for the scattering amplitude. Okay, so yeah, just to give you maybe a better idea of what happens when you get to the bottom of this recursion. So what kinds of graphs do you actually see at the bottom? So here's one example of BCFW graph. It comes from like this side, these kinds of graphs where I choose both the left and the right graph to be empty. That's always fine. Here's another term, again, coming from this sum, where I chose the left graph to be empty, and the right graph is this one. So I put that in here. And then again, like another kind of graph that comes from this term, or from this kind of sum, where I've chosen both the right and the left to be this one. Okay, so these are the sorts of graphs you see at the bottom of this recursion. Okay, so that's the BCFW recursion interpreted purely pictorially. At the bottom, it will give you an expression where every term is indexed by graphs. And that means that each BCFW expression also picks out for you some positoroid cells, which I'm going to call BCFW cells. Right, so the conjecture, kind of the guiding conjecture of Arkani-Hamed and Trnka, was that every BCFW expression gives you a tiling. So if you take those cells corresponding to the expression and you take their images under the Z tilde map, you will really get a tiling of the amplituhedron. Okay, and this is, like I said in the beginning, this is exactly the result I'm telling you about today. So yeah, so this is, we proved this. I should also mention that prior to the work with 6 authors, Chaim, Zvika, and Ran proved this conjecture for kind of a single BCFW expression, kind of the most standard one, maybe, I don't know. And then we together did it for every expression. Okay. Yes.
Again, speaking about this again, notion of tiling, you said you're not requiring that 2 cells intersect properly. If required, they add this requirement that intersections of 2 cells in a small cell.
Yeah, so
is that actually, I don't know, different examples that can kind of make a stronger identity?
Yeah, so the kind of, if you choose I well at each stage of this recursion, I think you can make it happen. Yeah, that's right. That one is good.
Like more, not just tiling, but triangulation.
Yeah, I mean, I don't think we've definitely, it's been checked that in codimension 1, the correct things happen. So if 2 tiles intersect in codimension 1, their intersection is another image of a positron cell. I think so. Yeah, so that's a good thing to say. Like, our definition of tiling is really motivated by this like physics application. As a mathematician, maybe one would want something stronger, like asking that intersections of tiles are again injected images of positoroid cells. That notion, as far as I know, is completely unexplored.
But you know, like for example, for maybe this might be a truth for some particular BCFW, because but if you we have some examples of some schemes where you have these twists, then it's kind of not doesn't satisfy this.
Yeah, almost all BCFW tilings will not be good, so there will be bad behavior at the boundary. Yeah, but there's the nicest ways of running the scheme would probably, hopefully, give you, yeah, things where intersections are also well behaved. Okay, so I'm going to focus most of the talk on kind of a tool we discovered along the way to proving this, which is that the BCFW recursion itself plays very nicely with the cluster algebra structure of GR4N. If you remember from Christine's talk, what that's like. Yeah, so I'll mostly be focusing on this, and that means that I'll mostly be focusing on the tiles themselves rather than the entire tiling. Okay. Yeah, so I guess actually this is a good place to stop if there are any other questions. I'm about to sort of get more the rest of the talk is sort of progressively more detailed. So this is a good place to ask me like big picture questions. All right. Oh yeah, go ahead.
Is there a geometric explanation of what's recursion? That has always bothered me.
Yeah, so I mean, kind of like the way that we prove that you actually get a tiling sort of gives a geometric meaning to this recursion. I mean, basically it's like you can split up the big amplituhedron into some coarse pieces, and each coarse piece, like one coarse piece will just correspond to all of these guys, and it will be isomorphic to a smaller amplituhedron. And another coarse piece will like kind of correspond to things in this sum with the same J. And that also will be isomorphic to a smaller, kind of maybe not quite isomorphic, but related to a smaller amplituhedron. Yeah. Anything else?
Just to verify, so why you put the first sign, sum with something?
Oh, why split this off?
I mean, why you cannot just use the right hand side?
Oh, so
Is this like case and L is J is empty?
no, because I'm actually adding a lollipop here, and I'm not doing anything like that over here. Yeah, so I sort of wrote it small without the lollipop, but I'm adding a new index there. That's not connected to anything. Yeah, I think this is a soft factor. Is that right? From physics, this is the soft factor component. Yeah. Okay. All right. So, right. So if you want to show that each BCFW expression produces a tiling, the first thing is just checking that all of the cells that kind of correspond to any term in any BCFW expression, their images are actually tiles. Okay, so here's such a cell. So here's a graph that shows up at the bottom of this recursion somewhere. And here's the corresponding cell in the Grassmannian. Right, and the first thing we prove is that the image of this cell is really a tile. So it's 4K dimensional, that's the right dimension, and the Z tilde is injective. Okay, so I want to think just a little bit about, okay, so we're trying to show that some map is injective, so we want to invert it, right? So we take the image of this positroid cell and we want to invert the Z tilde map. So we have some matrix or some point in the cell. We hit it with the Z tilde map, we get this by matrix multiplication. And now the question is, if someone just hands you this point, this Y, and the image Grassmannian, and you also know Z, how can you recover your original matrix? So how can you recover these parameters alpha through epsilon? So in other words, what function can I apply to Y in order to recover this alpha 1, beta 1, etc.? And the answer is the functions that you should use are cluster variables for GR4N. So yeah, not like really random functions, instead these like very special generators for this coordinate ring. Right, so to invert the Z tilde map, it turns out you need to use cluster, or like a very convenient choice. The only way we know how to do it is to use cluster variables. And a very closely related result, we kind of actually prove them both together, is that if you want to take one of these tiles and describe it just inside of GRKK plus 4 with no reference to your original TNN Grassmannian, you can do this. You can describe your tile as a semi-algebraic set using 5K compatible cluster variables for the Grassmannian. So remember, compatible means all of these cluster variables appear together in some cluster. Yeah, so for each tile, each BCFW tile, there's a collection of 5K compatible cluster variables. And by specifying the signs of those cluster variables, I can exactly cut out the tile of interest.
What's the explanation for the number 5?
Oh yeah, this is a lie, actually. I'm sorry. The 5K are really, yeah, it's 5K cluster monomials. And so then if you want to get down to cluster variables, which is possible, will be smaller. The explanation for this 5K cluster monomials is just that basically like the parametrizing matrices that I use for the BCFW cell, there's sort of 5 parameters for each row. And so I'm trying to like get those parameters back. And so yeah, there's always this like overall, I could always rescale each row if I wanted, but it's actually not good to do that for the proofs. So that's the reason for that. Okay. Right, and I'll just say, so we can give semi-algebraic descriptions of the tiles using compatible cluster variables. And one thing that implies is one of these cluster adjacency conjectures. I think it was the tree level cluster adjacency that Mark talked about yesterday. So from this semi-algebraic description, sort of immediate that the facets of the tile lie on hypersurfaces cut out by compatible cluster variables. Yeah, and so this was, I think the conjecture was originally made by Drummond, Foster, and Gerdegun in this context. Right, so we can also, so that's another nice thing, we can resolve this cluster adjacency conjecture. Okay, so yeah, these are the results I'm kind of going to dig into. Maybe I have already implicitly assumed everyone remembers Christina's discussion of the cluster structure and the Grassmannian very well. In case that's not true, I'm just going to quickly review it. Right, so she talked about GRKN, I'm just talking about GR4N. Right, so this cluster structure is a distinguished, usually infinite set of generators. Those are called cluster variables. Oops. And these are grouped into clusters of a certain size. Christina, I think, gave you a general construction for at least one cluster, but here's an example for GR4N. And right, the meat of this definition, or the meat of this statement, is that the clusters are not like arbitrary, but instead they're related by this mutation, which is a very rigid combinatorial operation. Okay, and right, if you remember from Christina's talk, so here's a cluster for GR47. It consists entirely of Pluker coordinates. Some mutations will take you to another seed consisting of entirely Pluker coordinates, but most seeds, infinitely many seeds for most GR4Ns, consist of non-Pluker coordinate cluster variables. So here's an example of a mutation you can do to get this function, which is a cluster variable, but is some quadratic difference of Plukers. Okay, right, and just as a reminder, yeah, I guess I should emphasize maybe something that Christina said, which is the vast majority of clusters for GR4N and most Grassmannians, we don't know anything about them. We can't characterize them. So yeah, there's in practice, no good way to verify if some element of the coordinate ring is a cluster variable or not. Right now, I said this already. The other thing you need to remember is that set of cluster variables are compatible if there's a cluster containing them all. And again, there's really not usually a good way of checking this except finding such a cluster, which is usually helpful. Okay, so brief review on cluster structure. Everyone is good? Okay, so yeah, let me return to the results I want to discuss. So I don't know if yeah, so I guess I have given this talk before, and someone has asked me, don't you have a typo here? Like, how are you taking cluster variables for GR4N and using them to talk about something inside of GRK k plus 4? Like, surely you've just gotten some indices mixed up. So that's the thing I want to explain now, that this statement actually does make sense. So the fastest way of saying this is that you can embed GRK k plus 4 into GR4N in a certain way that depends on Z. And then you can apply whatever functions on GR4N you want to GRK k plus 4 by just using this embedding. But let me give a little bit more detail about kind of what happens under this embedding. And what happens basically is twister coordinates come up. So Ron defined these, but I'll define them again. So what's a twister coordinate? So it's a function on GRK k plus 4. So pick some point in there. Also pick a Z matrix, just like for the amplituhedron, and fix 4 indices, I1 through I4. The twister coordinate of y, the y I1 through I4, is just the determinant of the matrix where I put y on top, followed by the I1th row of z, then the I2th, I3th, and I4th. Okay, and you can either just look at these as perfectly reasonable functions on grkk plus 4, or I can tell you this is exactly what happens when I embed grkk plus 4 into gr4n and then take a Plucher coordinate, like I evaluate a Plucher coordinate after doing that embedding. Okay, so these twistor coordinates have been around for a while, so it's sort of definitely not our idea to use them to talk about the amplituhedron. As you can see, the twistor coordinates, they involve Z, right? They're using some data about Z. And so they're just sort of, they turn out to be good for describing Z tilde images of things. Right. And so the way that I'm going to interpret a function on gr4n as a function on grkk plus 4 is I'm just going to replace each Plucher coordinate for gr4n with a twistor coordinate. Okay, so that's all I'm going to do. And so I'm going to keep saying cluster variable on gr4n, and I'm going to keep applying them to grkk plus 4 by doing this transformation without comment. Okay. Any questions? All right. So now this result should, all of the pieces should make sense. So I'm actually going to, so the thing I'm going to dig a little bit more into right now is actually not the injectivity argument, the inverting Z tilde, but instead the semi-algebraic description of each tile. The ideas involved are very similar for the two of them. It's just easier kind of to talk about the semi-algebraic description in a talk. Yeah, okay, so this is the thing I'm going to spend probably almost all of the rest of the talk on. That if you start with one of these graphs from the BCFW recursion, the image of the corresponding cell is a tile, and we have this nice semi-algebraic description in terms of compatible cluster variables for gr4n. I will get a little bit into the proof, but maybe before that, just why is this sort of thing a good theorem to have? The first is if you're only interested in proving that you've got tilings, one thing you have to understand is, well, you have to prove that the tiles in your tilings don't overlap. And the semi-algebraic description is very useful for this purpose, right? So if you know, oh, one tile, like this particular function is positive on this tile, and you can show, oh, that function is actually negative on the other one, then definitely they don't overlap. So it's very useful for that reason. Another reason that this sort of thing is useful is that inverting the Z tilde map, which is sort of like really closely related to the semi-algebraic description, inverting the Z tilde map gives you a way to define a top form on each tile, kind of by using a natural top form from the cell that it came from. And just doing this already gives a strong geometric connection to scattering amplitudes. And I guess the other thing is that this kind of semi-algebraic description is a step towards proving that these BCFW tiles, and maybe from there the whole amplituhedron, are positive geometries. Right, so if you want to prove something as a positive geometry, you need a semi-algebraic description, and this does that. And I should say, this top form you can define, that should probably be the canonical form of these if they're positive geometries. Okay, so now a little bit about the proof. So the definition of these graphs is recursive, and so our proof is also going to be recursive. I mean, it'd be really nice if you could do it directly, but we could do it recursively, so that's what we do. And the key step of the proof is to, well, understand the effect of doing the recursive step on the level of graphs. So, right, in this BCFW recursion, like the graphs that look like this, it's easy to understand what kind of effect that has on the tile, the corresponding tile. And this one is the more complicated one. This is where the meat is. So basically, okay, sorry. So the scenario that we're thinking about is we already have semi-algebraic descriptions of the tile corresponding to like this left graph. And we also already have a description of the tile corresponding to the right graph. And now we want to somehow upgrade the semi-algebraic descriptions for the two sides into a semi-algebraic description of this big, the tile corresponding to this big graph. So what we do is we define a map, psi, called product promotion. And this map is exactly the upgrade map. Okay, so it's a map between kind of like the GR4 for the left tile and the GR4 for the right tile to the GR4 for the big tile. And what does this map do? Well, okay, so for physicists, this is just the momentum twister version of the BCFW deformation. So this is in a paper of many authors, I think Arkani-Hamed, Borgeli, Cacciazzo, Caronwat, and Trnka. For mathematicians, what are we doing in this map? Okay, well, in this product, like the way that we're gluing these graphs together, there's 5 special indices, right? A, B, C, D, and N, which is the location that I put this like butterfly. And what this map is going to do is it's going to slightly change, basically like slightly change the columns of the matrix, like for this GR4, that involve the index, sorry, the column in position B. So if you have some matrix here, I'm going to change column B to a linear combination of columns B and A. And then this affects Pluker coordinates in some way. And for the right Grassmannian, I'm going to change both columns D and columns N to some linear combination of nearby columns. Okay, so on the level of Pluker coordinates, just maybe easier to think about, what does this map psi do? So it preserves almost all Pluker coordinates. The Pluker coordinates that are far away from like B, D, and N, those will just be preserved. But some Pluker coordinates will be changed to a quadratic difference in Plukers divided by a Pluker. So for example, if I'm looking at the Pluker coordinate with indices 1, 2, 3, B, this changes to this expression. And if I simplify, that turns into this. So this is a Pluker times Pluker minus Pluker times Pluker over Pluker. Okay, so that's what the map does. And the first thing you can do, like if you just look at this map, you can show that it's very, very well behaved with respect to the cluster structures on these Grassmannians. So this map, it's what's called a quasi-cluster homomorphism. What that means is if you hand me a cluster for the left Grassmannian and for the right Grassmannian, psi will send it to a collection of compatible cluster variables for the big Grassmannian. Okay, so yeah, so we've got this map psi. It kind of comes from some previous physics considerations. Like we didn't cook this up on our own. It really comes from what the physicists were doing to compute the BCFW recursion. And we can show that it behaves really well with respect to the cluster structure. And this psi map, the point is, it's exactly what we do to take the semi-algebraic description for the left and right tiles and upgrade them. So, right, so let me phrase this a different way. If someone hands you a BCFW graph like this, then I use psi to recursively define 5K compatible cluster variables. Okay, and that's not quite 5K, some number close to 5K compatible cluster variables that will cut out my corresponding tile. Okay, so a little bit, I'm not going to give that much detail about what these are. I'll just kind of give some examples. So 5 of these cluster variables are very easy to describe. So if your graph, like the last thing you did was this kind of product using indices A, B, C, D, and N, 5 of your cluster variables will be just the twister coordinates using 4 out of the 5 indices. There are 5 of those. Okay, and then the remaining cluster variables you want are just obtained from the ones you got from GL and GR by applying this psi map. Right, so quick example. If you handed me this BCFW graph, then the collection of cluster variables I would get, well, this just looks like the butterfly. There's nothing else, so I just get the 5 easy cluster variables. Similar with this guy, just the 5 easy ones. And then I apply, right, so then to get the functions for this one, I have the 5 easy cluster variables and then psi applied to both the red and lavender easy cluster variables. All right. And right, so the theorem is that this is exactly the correct thing to do. So these compatible cluster variables, there are some recursively defined signs, and the points in GRKK plus 4, on which the cluster variables have those signs, is exactly the tile. And so, yeah, just to give you maybe an idea of the signs, for the easy cluster variables, they're really easy to predict. I think I wrote things in a funny order here, but for the easy cluster variables, it's just alternating, like plus, minus, plus, minus, plus, as long as you put them in the right order. And then the signs change when you apply the psi map. This change is easy to write down in a paper and cruel to expose you to in a talk. It depends a bit on the degree of, it depends a bit on the degree of the variable that you're applying psi to. Okay, so I think that's all I wanted to say. Yeah, so that's all I wanted to say about the tilings. About the tiles. I guess I'll add, so all of this was recursive because we wanted to deal with arbitrary ways of running BCFW. Oh yeah, go ahead.
How do you know this algorithm? Suppose I replace the diagram in the middle by something else. Is there still a map?
Oh, that's a really good question.
In general,
Oops.
Yeah, it still produce a compatible cluster variable.
Yeah, so that's a really great question. So you're asking, like, what if I change this butterfly? Yeah, we're thinking about that right now. Yeah, so this is all you need for BCFW, but there are tiles that aren't BCFW tiles. And so one could imagine maybe you can run a similar thing for those. So we're optimistic that it will work out. Yeah. Any other questions? All right. Yeah, so I should say, right. If you decide, okay, maybe I don't care about all BCFW tiles, I just care about the ones that come from like the nicest, the standard way of running the recursion, we can give things that are non-recursive. So in that situation, right, so this I was just like, oh, this is recursively defined, this is recursively defined. If you specialize to these standard BCFW tiles, we can give just completely explicit formulas for these cluster variables and completely explicit formulas for these signs. Okay, yeah, I guess I should also say, you could also ask like, which of these cluster variables cut out actually a facet of the tile? And the general, we give if you want to know that information, you should look at our second paper. Yeah, so again, sort of in this standard, the nicest way of running the recursion case, we can give like a really explicit list of which ones cut out facets. And in the recursive case, we have some characterization, which is a little harder to state. Okay, so just to wrap up, I just wanted to say a little bit about tilings. So, right, the result on tilings is that if you have, just say it one more time, if you have a fixed BCFW expression and you take all of the graphs indexing terms of that expression, the images of the corresponding positroid cells, so the corresponding tiles, they actually do form a tiling. And what those collections look like, well, you can really just read it directly off of the recursion. There's a lot of details about exactly how to fill in the two blobs. But yeah, so these are what the collections look like. And I just want to say, like, not very many words about how one actually proves this. So the first thing, okay, so we know we have a collection of tiles. We want to show they form a tiling. So the first thing is to just show that they're disjoint. And basically, the idea for this is really to utilize the semi-algebraic description in exactly the way I said before. So we know that certain functions have a specified sign on each one of these tiles. And that characterizes the tiles completely. So then you just have to think a bit to make sure that that actually means that they're far away from each other, that there's like some hypersurface between them, basically. Right, for the second piece, you want to show that the images of these tiles, the tiles, the union of the tiles is the entire amplituhedron. Right, and so to do this, what we do is we break the amplituhedron up into kind of bigger pieces, so pieces which are much bigger than a tile. Okay, so if you're really an expert, the pieces that we use, they're images of the positroid cells that we get like this, where in the left and right, I put like a graph for the top cell. So these are much, much bigger than tiles, but yeah, they're still like images of positroid cells. And then those pieces are kind of more closely related to smaller amplituhedra, like for smaller K and N. And so it's just easier to show that they decompose into tiles. Yeah, so there is of course an inductive component where we're going to use induction to show that the tiles cover each piece. That's like the image of this sort of thing. Yeah, so that's all I want to say about tilings. Yeah, and I think given the time, rather than summarizing, I'll just leave the summary on the slide and I'll stop there. Thanks so much for your attention.